A bountiful day to us all Pilarians. I am Hans Lapesora.
And I am Kitara Castro, and we are your math reporters for today. Making predictions using regression analysis. That is our topic for today.
For our table of contents, we have History of Correlation and Regression Analysis, Correlation Analysis Recap, What is Regression Analysis, Types of Variables, Forms of Regression Analysis, and the last, the Regression Analysis example using simple linear.
Let us discuss the history of correlation and regression analysis. Some may not know him, but he is Sir Francis Galton, born on February 16, 1822, and died on January 17, 1911. Was an English polymath in the Victorian era. Early on, Sir Francis Galton developed correlation. Galton, Charles Darwin's close cousin, accomplished a lot. He studied medicine, journeyed to Africa, published in the fields of psychology and anthropology, and created visual methods for mapping the weather. The first time Galton wrote about correlation was in 1888. Two variable organs are said to be correlated when the variation of the one is accompanied on the average by more or less variation of the other, and in the same direction. It is easy to see that correlation must be the consequence of the variations of the two organs being partly due to common causes. Galton began writing correlation as correlation in 1889 and had developed a fascination with fingerprints. The final substantial study Galton would write on the topic would be his 1890 explanation of how he developed correlation. Galton's friend and colleague Karl Pearson, who is also the father of Egon Pearson, followed the improvement of correlation with such energy that the statistics are, which Pearson termed the Galton coefficient of reversion and Galton dubbed the index of correlation, is known as Pearson's R.
Thank you for that wonderful information, Kitara. Now, let us move on and let us have a recap about correlation analysis because I believe that correlation and regression analysis are like siblings in math. It is a statistical approach known as correlation, shows how closely two or more variables change with respect to one another. A positive correlation shows how much two variables change simultaneously, whereas a negative correlation shows how much one variable rises as the other one falls. So, in other words, it is a statistical method called correlation can be used to determine if and how strongly two variables are related to one another. Your data may contain correlations that weren't expected even though this correlation is quite clear. You can also be aware that correlations exist but be unsure of which ones are the strongest. Clever correlation analysis can help you comprehend your data more. When the values increase together, the correlation is positive or direct, and when the correlation is referred to as inverse or opposing correlation, when one value falls as the other rises. So, some may ask, Hans, what is the relation of correlation and regression analysis to each other? First of all, great question. Well, the answer to that is very simple. As opposed to regression, which expresses the relationship as an equation, correlation measures the strength of the linear relationship between two variables.
Very well said, Hans. Now let us proceed to our main performance. What is regression analysis? Regression analysis is one of the most commonly used statistical techniques in social and behavioral sciences, as well as in physical sciences, which involves identifying and evaluating the relationship between a dependent variable and one or more independent variables, which are also called predictor or explanatory variables. It is especially helpful for determining and making adjustments. An estimated regression equation is created using estimates of the parameter, values, and model of the relationship that is hypothesized. The model is then put through a number of tests to see if it is effective. The estimated regression equation can be used to forecast the value of the dependent variable given values for the independent variables if the model is judged to be satisfactory. Regression analysis may be used to produce predictions without necessarily projecting the future. Instead, you make predictions about the dependent variable's mean based on the independent variable's values. It is possible to determine statistically which of those factors actually has an effect by using regression analysis. It responds to the questions: what elements are most crucial? Which may we disregard? What connections do the elements have with one another? The most crucial question is how confident we are in each of these characteristics, and those factors are called variables. There are two types of variables in regression analysis. Independent variables are characteristics that can be measured directly. These variables are also called predictor or explanatory variables, used to predict or explain the behavior of the dependent variable. A dependent variable is a character whose value depends on the values of independent variable. Note that there can only be one dependent variable, but there can be more than one independent variable.
Now, for the forms of regression analysis, we have three types, which are simple linear regression, multiple linear regression, and logistic regression. In simple linear regression, the dependent variable is inferred using just one independent variable. For example, when we want to predict the grades of Verhendel-Pilar students, we only use one variable, either the amount of sleep, or the daily study hours, or the age of a person. In multiple linear regression, we use a number of independent variables, such as the quantity of sleep, the number of hours a person studies each day, and their age, to infer our independent variable. Therefore, the difference between simple and multiple linear regression is that in the former, only one independent variable is used, while in the latter, multiple independent variables are used. Contrarily, logistic regression is used when the dependent variable is categorical. For instance, when attempting to determine whether a person is at high risk of depression or not, logistic regression is used whenever there is a chance of receiving a yes or no response. All of that, but today, we are only going to discuss simple linear regression. So let us say, for example, that the grade level is our dependent variable and our independent variable is the average amount of sleep. A Pilarian researcher surveyed grades 1 to 12 students and their average amount of sleep. We gathered samples from Pilarians, and this is what we got from our gathering. And this is what it looks like when we plot the samples to a graph. So, the first thing we're going to do is we're going to make a table where we have 4 columns. The first column is x, second is y, third is xy, and the fourth is x squared. In the column x, we're going to insert the dependent variable, which are the grade level. In the column y, we're going to insert the dependent variable, which are the average amount of sleep. In the third column, we are going to multiply x and y. In the fourth column, we're going to square x. Now, to find the equation, we need the sum of the value x, the sum of the y value, the sum of the x times y value, and the sum of the x squared value. In order to find, we just have to add all of the numbers under that column. So when we added the numbers, we found out that the sum of the x values is 124, and the sum of the y values is 141, and the sum of the xy values is 723, and last but not the least, the sum of the x squared values is 1038. So, everyone knows the slope formula, which is y equals mx plus b. Now, in statistics, it is more commonly known as y equals b0 plus b1 x. So we need to know that the slope, or m, is b1 and the y-intercept, or b, is equals to b0. So let us find out how we can get the slope in this example. So the formula for slope is n times the sum of xy values minus the sum of x values times the sum of y values over n times the sum of x squared values minus the quantity of the sum of x values squared. N is the number of values we have in our data, so it is 20. So if we substitute our given to the formula, we will get 20 times 723 minus 124 times 141 over 20 times 1038 minus 124 squared. And if we simplify that, we will get negative 3024 over 5384. And we will have our slope, which is negative 0.561664 and etc. Now next, we will calculate our y-intercept. In order to get the y-intercept, we have the formula of the sum of y values minus slope times the sum of y values over n. So if we substitute our given, we will get 141 minus negative 0.5616 and etc. times 124 over 20. And if we simplify that, we will get 10.532317986. So in order to write the linear equation, we will need to plug in our m value and our b value into the slope-intercept equation. So we will have the negative 0.56 as our slope and 10.53 as our intercept. We don't need to use the exact equation. So let us apply the equation to the numbers. So we have grade 1 students as our x value. If we simplify that, we will get an answer of 9.97. So in conclusion, grade 1 students have an average nap time of 9.97 hours. Next, we have the grade 5 as our x value. If we simplify that, we will get an answer of 7.73. So in conclusion, grade 5 students have an average sleep of 7.73 hours. So for our final application, we have grade 10 students as our x value. If we simplify that, we will get an answer of 4.93 hours, which concludes that the grade 10 students have an average time of sleep of 7.93 hours. Did you learn anything from our report, or do you have any questions? Whatever it is, please message us if you want to clear your curiosity. That is all for today, folks. Thank you for listening and God bless us all.